In the previous video, we were just talking about how the elephant was definitely an outlier. I should move this so you can see it. The elephant was an outlier in the context of the data. However, it did not have the largest residual value here. It only had a value of 98. And so there are other animals with a larger residual, which means a bigger gap between the actual and the fitted value. And so the next one, letter I, says, well, okay, fine. If it's not the elephant, then which one does? Which animal does have the largest residual? Hint, click on the most extreme residual in the residual plot to identify the case. So we can do that. This is looking like the most extreme to me. And yep, lo and behold, it's the giraffe. So the giraffe has, look at the size of that residual. It's like 272. That's a huge gap. Okay, so the giraffe has the largest residual. Is its gestation period longer or shorter than expected for an animal with its longevity? And if you look at the chart, you see that the fitted value is 152, and that is much less than it would have been predicted. Okay, so the actual gestation is much longer. The actual gestation is 425. The predicted gestation was 152.9. So the gestation period is actually much longer than predicted. Next, click to highlight the draft data point on the scatter plot or in the case table and eliminate it. Check the revised equation in the regression line. So we're going to see the impact of removing the giraffe. So here's giraffe, and we're going to delete it. Delete the case. And we see what happens. The gestation equation changes to 14.1 on this one. And R squared is 0.50. So okay, I'll record that. Regression line, giraffe omitted. I got 14.1 times the longevity, not log. And R squared was 0.50. Okay, so that means the slope went up and the determination coefficient went up, so we have a higher percentage on the line. The following scatter plot displays the original and both regression lines. Is this new regression line substantially different? You can kind of see here there are two regression lines. Is it substantially different? No, it isn't. So changing the giraffe didn't change that much, is what they're getting at here. Okay, put the giraffe back. Hit edit, undo. Okay, giraffe, you're back. Then eliminate the elephant. Oh, okay, now let's see. So we took out the giraffe was the one with the largest residual value, and now we're going to take out the elephant. There we go. Delete the case. And that changes our equation a little bit. I feel like I should have changed it much more. Okay. So I've got, what, 14.0 times longevity, and R squared is 0.25, which is much lower. So the regression line was 14.0 times the longevity, and the R squared was 0.25. So that's only 25% match. Okay, so the scatter plot below displays the original data with the actual regression line, and the elephant's gone. In which case did the removal of one animal affect it more? We would say the elephant removal affected the regression line more. The elephant, as you recall, is an outlier, but it did not have the highest residual. Okay, so now we're going to learn about something called an influential observation. In the context of least squares regression, an influential observation is one whose removal would substantially affect the regression line. So in this case, it was the elephant. Observations with extreme values of the predictor variable are potentially influential. So extreme values of the predictor variable. The predictor variable is the x value. So extreme values of x. Removing the elephant from the analysis has a considerable effect on the least squares line. Removing the giraffe did not. So we would call that an influential observation. Okay, so investigate further. We're going to put the elephant back. Let it undo. Okay, there it goes. And we're going to click on the elephant's data point and drag it up and down. And they want you to see the impact. It's changing a lot, right? Okay. To give different gestation periods. Okay, it's changing a little bit. How does the least squares line react? Well, the slope is going down, right? Okay. Compare this to how the line changes when the point, like the giraffe, is moved up and down. So I guess we'll put the elephant back, right? And let's move the giraffe. See? And do we see the line changing very much? No, the line isn't really changing as much, I guess, is what we're trying to say here. Okay. All right. So, well, the elephant point affects the slope more than the giraffe point. Okay. 11-2. Residual plots. So below are 4 scatter plots with regression lines drawn in. And the goal, so what do we got? We've got miles per gallon rating versus weight for sports cars. Distance from the sun versus the position of the planet. Rent versus price for monopoly. And airfare versus distance for the selected destinations. And you're supposed to compare this to the residuals on the next page. I'm going to shrink this so that we can kind of see more. Let's see what we can do here. Okay, so hopefully this helps a little bit. Move this. Come on. Okay, so on the top here, we have the scatter plots. And on the bottom, on the next page, 246, we have the residual plots. And what you're trying to do is figure out which scatter plot goes with which residual plot. Okay, so I'm kind of looking at this, and I see when I'm looking here at this one that the actual values and the fitted values aren't really that far. You see those dots are pretty close, and so the residuals, I think, are not going, they're not really any kind of a pattern. It's kind of all over the place. Okay, so to me that's matching with this one, so that would be D. This would go with 1. Number 2 is looking kind of interesting, right? And so we see what's happening there. Your residuals it starts out being farther away, and then it gets closer. Okay, and then all of a sudden your values get far away again, right? They're much less than the actual values, and then they go back and they're higher than the actual values. So that would be like letter B. So this is 2, this is B. Number 3, they're super close, right? And so you have sort of a positive residual, and then it kind of barely goes negative, and maybe a little bit more, and then it kind of pops up to positive again. And so that would go with this one here. So A and 3 match. And then obviously the last one has to go with C, but we can kind of see why. You have a negative residual, a positive, 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 negative, positive, negative. And so that would go along with this one. What's important when you're looking at these residual graphs is where the 0 is. Okay, because any dot that is above the regression line has a positive residual, and the dots that are below have a negative. So 4 goes with C, and this would go with a 4. Okay, so we match that up. And the next thing that they tell us to do, match up the data with the following descriptions. Here I am down here. For which one are the residuals randomly scattered? And we would say D. The residuals are largely randomly scattered except for 2 very large negative residuals. That would be C. The residuals show a distinct curved pattern. That would definitely be B. And the residuals show a clear linear pattern with 3 severe outliers, and that would be A. Look back at the original scatter plot with the regression lines drawn in, and which 2 plots to the line summarize the relationship as well as possible. So if you look back at the plots, plots 1 and 4 summarize the data best, and 2 and 3 are better described by a curve. The line really doesn't do much for you there if you look back. Okay, if you look at 2 and 3, it's more curvy. I guess you could sort of argue 3, but 1 and 4, I guess, are better for the linear regression, according to the residuals. Okay, so do these scatter plots where the lines summarized correspond to the highest values of R squared? And no, because there are more points closer to the line in the non-descriptive plots. So what you want to remember here is that R squared is how close the points are to the line. Okay? All right. That's the percentage. It's also called the percentage of variability. That's a topic 10 concept. All right, these examples show the residual plots can indicate when a linear model does not adequately describe the relationship in the data. When a straight line is a reasonable model, the residual plot should reveal a random pattern. When a nonlinear model is better, then the residual plot reveals a different kind of pattern. Note, value of R squared alone is not sufficient. Okay? So what we're taking away from this is a random residual plot means that the line is a reasonable model. Okay, and that is it. That is it for topic 11, and we are done with unit 3.